Hey everybody, and welcome. What I would like to do for you today is demonstrate a very simple technique for measuring and characterizing a small length of coaxial cable transmission line. So you see, I have here a mystery cable. I don't necessarily know anything there is to anything about this cable. I don't know its impedance, I don't know the velocity of propagation, and I don't know its characteristic capacitance or inductance. But I would like to measure those parameters somehow using some various household products like this NanoVNA here. Now, the only thing I know about this cable is its length, which I can measure with a ruler, and I have found it to be exactly 5 feet. Now, hypothetically, I could look at the markings on this cable, and it'll say RG174, and I can then go online and look up the parameters of this cable on some online data sheet. However, maybe for whatever reason, that's not an option. Say, for example, the markings have been worn off, or maybe I just don't trust the information on that data sheet, and so I would like to validate it for myself. So what follows is just going to be a simple tutorial on how to use nothing but a NanoVNA to measure and characterize all of those parameters for this little piece of coaxial cable transmission line. Okay, so as you can see, I've written down the 4 defining parameters for any transmission line. We have L prime, which is the characteristic inductance. We have C prime, which is the characteristic capacitance. We have R prime, which is the characteristic resistance. And we have G prime, which is the characteristic conductance. Now, in practice, R prime and G prime are generally going to be very small to the point of being negligible. Because after all, what good is a coaxial cable transmission line if it is extremely lossy? So what this technique is going to do is we're just going to measure essentially L prime and C prime and ignore the effects of these 2 parameters because in any real cable, they will generally be very small in relation to these other 2. So once I have L prime and C prime, I can, in principle, calculate Z naught, which is equal to the square root of L prime divided by C prime, right? So if I know L prime and C prime, I can presumably calculate the characteristic impedance. Likewise, we have the phase velocity, V sub p, which is equal to 1 divided by the square root of L prime times C prime. So if I know these 2 parameters, I also can derive these 2 over here. And again, this assumes that these 2 parameters are small to the point of being negligible. So in principle, I could hypothetically measure these and derive these, but it turns out it's not really as simple as it sounds, which will be explained later. So what we're really going to do is actually measure C prime, and then we're going to measure V sub p. And then given these 2 parameters, we are then going to derive the characteristic impedance Z naught and the characteristic inductance L prime. So let's start by doing a little bit of substitution. I'm going to solve for L prime in terms of V sub p and C prime. And what I will find is that L prime satisfies 1 divided by V sub p squared times C prime. So you notice if I know these 2 parameters, I can effectively calculate L prime over here. Likewise, if I then do a little bit of substitution and calculate Z naught in terms of these 2 parameters, you find that Z naught is equal to 1 divided by V sub p times C prime. So just the little square goes away. So these are actually the 2 equations we're going to use. Because it's actually not as easy as you might think to measure Z naught, and you can, in a sense, measure L prime, but there's some frequency issues which we'll discuss later. So let's go ahead and begin with this process now. Okay, so you notice I've got my NanoVNA here, and I've done something very special, and that is I've set it to a very low frequency range. You see how it's starting at 50 kilohertz and then going to 200 kilohertz, okay? So the actual frequency span doesn't matter too much, just so long as it's something generally very low, say below 0.5 megahertz. So what I'm gonna do is just plug in my mystery cable, just like this. And you can see that the NanoVNA, all it sees is an open circuit. Barely anything has changed. But it's been tweaked just a tiny bit, and it will actually return what it thinks is the equivalent capacitance of this load. So what's happening is it's sending out a signal which bounces off the open circuit here and comes back. But the frequency is so small, that means the wavelength is gigantic. Therefore, the phase error that accumulates from this back and forth propagation is essentially negligible right now. Okay, so we can pretend that that is basically zero, which means all it is seeing is the equivalent capacitance of this lump of cable here, which it calculates for you automatically on the Smith chart. And if you look very closely, it's coming in at about 155 picofarad. Okay, so, and you notice also I can scan around in frequency and it just kind of bumps up and down by a couple of picofarad. So it's actually a very interesting measurement you can do, that your NanoVNA will act as a very strong and accurate capacitance meter by just reading any sort of lumped element at a low frequency. So all you have to do then is come back here, and we have our capacitance, C prime, is equal to 155 picofarads. But remember, it's also divided by a 5-foot length of cable, because this is a per unit length parameter. So divided by 5 foot. And if you do the math, 5 feet is about a little over 1.5 meters. You come out to about 101 picofarads per meter for our capacitance. And that's a very accurate and reliable measurement of C prime for any lump of cable, so long as the frequency is very, very low. And incidentally, this is exactly the specification in the datasheet for this lump of cable, so we can trust that it's a pretty accurate measurement. Now, with that information in mind, you might be tempted to try the following measurement. I'm going to go ahead and grab a little barrel connector, like this guy here, and attach it to the load. And now I'm going to take my calibrated short circuit here and attach this to the end as well. And you can see how the Smith chart immediately jumped to the left to indicate the short circuit here. And in fact, the NanoVNA is smart enough to recognize that this is now essentially acting like a very big lumped inductance. And so it returns a value of about 487 nanohenries. The problem is this measurement of inductance changes with frequency. Since we are at a very low frequency, the true inductance of this cable is actually higher than it would be if we were operating at, say, 100 megahertz. So this is technically an accurate measurement, but it does not reflect the true inductance of this cable when you operate it at higher frequencies. So the reason for that is actually the skin effect. That is, at low frequency, the current inside the conductors wants to flow throughout the entire volume of the copper on the inner conductor and on the shield. When you go to higher frequency, that current then gets squished to the outer edges of all the conductors, which actually manifests as a reduction in the inductance. So yes, this is technically an accurate measurement of inductance, but you cannot trust it at higher frequencies because it will in fact physically change. The problem, though, is that you can't just crank up the frequency and do this measurement, because then you'll have the phase issue to deal with here in terms of that phase error accumulating as the signal goes down and back. So yes, this is actually an accurate measurement, but we need some way to characterize this thing at higher frequency. That is to say, we can't trust our inductance measurement at low frequency or expect it to remain consistent as we go into higher frequencies. So instead, what we're going to do is measure the velocity of propagation at a high frequency. So this is accomplished as follows. Okay, so you notice I've removed the short circuit from my load here, which means I am now back to the open circuit condition on my Smith chart here. Now what I'm going to do is recall one of my settings here. And you can see all I've done is increase the stop frequency so that it's going from 50 kilohertz all the way out to 100 megahertz. Okay, so this is important because what I need is a high enough frequency so that I can figure out at what point does this open circuit now appear to be a short circuit from the perspective of channel 0. So I'm just going to dial it on in, and you can see at about 33 megahertz, that is where it's gone from open circuit to short circuit. Now this particular frequency is very special because what is happening is the length of this cable is now exactly 1/4 of a wavelength. That means it's going down and accumulating 90 degrees of phase shift and then bouncing back again to accumulate another 90 degrees to give me a full shift of 180 degrees, or I guess technically negative 180 degrees because it went clockwise. So if you want to do that in radians, we have accumulated a phase shift of pi radians here. So it's pi over 2 down, pi over 2 back, and pi total. So how is that information useful? Now remember that the electrical length of any transmission line is equal to beta times L, where beta is called the propagation constant, which is equal to omega divided by the phase velocity times L, where omega is the angular frequency, v sub p is the phase velocity, which if we convert to regular frequency, you get 2 times pi times f times L divided by v sub p. That is the electrical length of this particular length of cable here, which at this frequency, remember, is exactly negative 90 degrees or 90 degrees. So 90 degrees down, 90 degrees back is 180 degrees, or down and back is pi. So the length here is pi over 2 radians in electrical length. So all I'm going to do is solve for v sub p. And what you find is that v sub p is equal to 4 times f times L. Just like that. So very simple. When the length is exactly a quarter wave, or the length of the cable is 1/4 wavelength, then we know that the velocity of propagation is 4 times f times L. So if you plug in the values, it's about 33 megahertz here and 1.52 meters here, you come out with roughly, say, 0.67 times the speed of light, which is about 2.01 times 10 to the 8th meters per second. Okay, so you can plug in the values that I measured here, and this is what you would get. So remember also that the characteristic capacitance was C prime equal to 101 picofarad per meter. So given those two bits of information, all I have to do is a little bit of math and I can calculate the characteristic impedance, which is 1 divided by V sub p times C prime, which you plug in these two values here, and I've already done the numbers offline, and you come out to something like 49.2 ohms given the values that I've measured here, or approximately, if you round a little bit, 50 ohms plus or minus maybe an ohm, half an ohm, depending on the precision of your measurement there. So that's pretty good, which is what we'd expect for most cable. But of course, if this was a 75 ohm cable, you would get something very close to 75 ohms as well. Likewise, if I want to calculate the characteristic inductance, I can just say 1 over V sub p squared times C prime, and you plug in all the numbers, and you'll get something on the order of about 245 nanohenries per meter, which again, I already did this calculation offline, and you can double check my values here. You'll get something reasonably close. So there you go. I now know pretty much everything there is to know about this little length of coaxial cable. I know its impedance, I know the characteristic impedance, I know the phase velocity, I know its characteristic capacitance, and I know its characteristic inductance. Okay? And all it took was 2 simple measurements and a little bit of math. So thank you for listening, and I hope that's useful for you in your own transmission line work.